Deep in the constellation of Volans, 34 light years from where you're sitting right now, something extraordinary is quietly orbiting a small red star. It's a world that might just change everything we thought we knew about where life could exist in our cosmic neighborhood. Tonight, we're going to take a gentle journey to one of the most intriguing planetary systems ever discovered, where 5 worlds dance around their crimson sun, and one of them sits in that precious zone where liquid water could flow. I'm curious, where in the world are you listening from tonight? And as you settle in, perhaps with a warm cup of tea or curled up under your favorite blanket, imagine for a moment that you could peer through the most powerful telescopes humanity has ever built. What you'd see would challenge everything our ancestors believed about the rarity of worlds like our own. Because out there, in a system called L9859, astronomers have found something that makes their hearts race with possibility. If you find this cosmic exploration soothing, if the mysteries of distant worlds help you drift toward peaceful sleep, I'd be ever so grateful if you gave this video a gentle tap of approval. It helps other stargazers find their way to this quiet corner of wonder, and perhaps they too need a moment of celestial calm after a long day. Now, I do hope the universe isn't so fascinating tonight that it keeps you awake, but if it does, well, at least you'll have learned something remarkable about our place in the grand tapestry of existence. So let's dim the lights, slow our breathing, and venture forth into the darkness between stars, because sometimes the most beautiful discoveries are found in the quietest places. The story of L9859 begins not with a dramatic supernova or the collision of galaxies, but with something far more subtle and profound. It starts with the patient work of astronomers who spend their nights staring at a single point of light, watching for the tiniest dimming that might reveal worlds beyond our solar system. And what they found around this unassuming red dwarf star has rewritten our understanding of planetary neighborhoods. L9859 isn't much to look at, really. It's what astronomers call an M dwarf, a red star so small and cool that it makes our sun look like a blazing giant. With only about 32% of our sun's mass and a surface temperature of just over 3,000 Kelvin, it's the kind of star that burns quietly for trillions of years. These red dwarfs are the universe's marathon runners, steady and enduring, outlasting even the most brilliant blue giants by eons. But here's the thing about red dwarf stars that makes them so compelling in our search for life. They're everywhere. In fact, they make up roughly 3/4 of all the stars in our galaxy. Think about that for a moment. If you could somehow visit every star in the Milky Way, 3 out of every 4 would be these small, red, long-lived suns. And around many of them, as we're discovering with increasing frequency, orbit worlds that might harbour the conditions for life. The L9859 system was first brought to our attention by NASA's Transiting Exoplanet Survey satellite, lovingly known as TESS. Launched in 2018, this remarkable spacecraft has been quietly revolutionizing our understanding of nearby worlds by monitoring the brightness of hundreds of thousands of stars simultaneously. TESS watches for transits, those magical moments when a planet passes directly between its star and our telescopes, causing a tiny but measurable dimming of starlight. In March 2019, TESS announced something remarkable. Around the red dwarf L9859, it had detected not 1, not 2, but 3 small worlds crossing the face of their star. These weren't the bloated gas giants that had dominated early exoplanet discoveries. These were small, rocky planets, worlds that in size and composition might not be entirely unlike our own Earth. But the story was far from over. As astronomers turned their most sophisticated instruments toward this system, they began to uncover layers of complexity that would make L9859 one of the most thoroughly studied multi-planet systems around a red dwarf star. Using ground-based spectrographs with names like HARPS and Espresso, instruments so sensitive they can detect the gravitational wobble of a star caused by a planet smaller than Earth, they found evidence of additional worlds. The discovery process itself reads like a detective story. While the first 3 planets announced themselves through their transits, casting shadows as they passed in front of their star, The outer planets were far more secretive. They don't transit from our perspective, which means they never pass directly between L9859 and Earth. Instead, they revealed themselves through the subtle gravitational dance they perform with their host star. Imagine trying to deduce the presence of an invisible dancer by watching their partner's movements on a darkened stage. That's essentially what astronomers did with L9859. By measuring tiny shifts in the star's light caused by the Doppler effect, as the star is tugged ever so slightly back and forth by the gravitational pull of its planets, they were able to infer the presence of worlds too distant or too small to see directly. This technique, called the radial velocity method, requires extraordinary precision. We're talking about detecting stellar motions of just a few meters per second, comparable to a person's walking pace. To put this in perspective, imagine standing on a mountaintop and trying to measure the sway caused by an ant crawling on the opposite side. That's the level of sensitivity required to find Earth-sized planets around nearby stars. The breakthrough came through something called line-by-line radial velocity analysis, a novel technique that squeezes every photon of information from stellar spectra. By analysing thousands of individual spectral lines simultaneously, astronomers can achieve precisions that were unimaginable just a decade ago. It's this technological wizardry that allowed them to confirm the existence of a fifth planet in the L9859 system, one that would prove to be perhaps the most intriguing of all. L9859F, as this world is now known, orbits its red dwarf star once every 23 days. With a minimum mass of about 3 Earth masses, it falls into that fascinating category of planets known as super-Earths. These are worlds larger than our own planet, but smaller than the ice giants Neptune and Uranus. They represent a class of planet that doesn't exist in our solar system, yet appears to be extraordinarily common throughout the galaxy. What makes L9859F particularly special isn't just its size or its 23-day year, it's where it orbits. This world sits squarely within what astronomers call the habitable zone, that precious region around a star where temperatures might allow liquid water to exist on a planet's surface. It's sometimes called the Goldilocks zone, because like the porridge in the fairy tale, it's not too hot, not too cold, but just right. Around a red dwarf star like L9859, the habitable zone is much closer than it would be around our Sun. While Earth orbits at a distance of about 93 million miles from our star, the habitable zone around L9859 extends from about 7 million miles to 15 million miles from the star. This means that L9859F, despite receiving roughly the same amount of stellar energy that Earth receives from the Sun, completes its orbit in less than a month. The entire L9859 planetary system is remarkably compact. All 5 known worlds orbit closer to their star than Mercury does to our Sun, yet they maintain stable, nearly circular orbits that have persisted for millions or billions of years. This orbital architecture creates a gravitational symphony, where each planet influences its neighbours in a delicate cosmic dance. The inner worlds of the system tell their own fascinating story. L9859b, the innermost planet, is slightly smaller than Earth, but orbits its star every 2.25 days. The intense gravitational interactions in this tightly packed system generate what astronomers call tidal heating within this world, potentially creating volcanic activity comparable to what we see on Jupiter's moon Io. This constant kneading by gravitational forces could maintain geological activity that might contribute to atmospheric processes. Moving outward, we find L9859c, a world about 1 1/3 times Earth's radius, completing its orbit every 3.7 days. Then comes L9859d, nearly 2/3 larger than Earth, with an orbital period of 7.5 days. This planet has captured particular attention because of its unusually low density, suggesting it might be what scientists call a water world, possibly covered by deep global oceans that could comprise up to 30% of the planet's total mass. The diversity within this single planetary system is remarkable. We have worlds that range from potentially volcanic hellscapes to possible ocean planets, all orbiting within a space smaller than the orbit of Mercury. It's like finding an entire solar system compressed into our sun's front yard, each world telling its own unique story of formation and evolution. What's particularly intriguing about the L9859 system is how it challenges our assumptions about planetary formation around red dwarf stars. Computer simulations suggest that more than 90% of Earth-sized planets around such stars should be at least 10% water by mass. This means that rather than finding rocky terrestrial worlds like Earth, we might be discovering predominantly water worlds, planets covered by single, globe-spanning oceans. The implications of this are profound. While water is essential for life as we know it, water worlds present their own unique challenges and opportunities for biology. Deep oceans might lack the geological processes that help regulate climate on Earth, but they could also provide stable environments insulated from the harsh radiation that red dwarf stars sometimes produce during violent stellar flares. Recent observations with the James Webb Space Telescope have begun to peer into the atmospheres of these distant worlds, searching for the chemical fingerprints that might reveal their true nature. Early results suggest that L9859d might possess a sulfur-rich atmosphere, possibly indicating active volcanism or unique atmospheric chemistry. Meanwhile, the search continues for signs of water vapor, carbon dioxide, and other gases that might tell us whether these worlds could harbor the conditions necessary for life. The story of L9859 is still being written. Each new observation, each refinement in our measurements, adds another chapter to our understanding of this remarkable system. As we've learned more about these 5 worlds, we've discovered that they represent something like a laboratory for studying planetary formation and evolution, all conveniently located in our cosmic backyard. The beauty of studying a system like L9859 lies not just in what we've discovered, but in how we've discovered it. The techniques that revealed these worlds represent some of the most sophisticated detective work in the history of astronomy, requiring instruments so sensitive they can measure stellar wobbles, smaller than the width of a human hair seen from across a football field. Consider for a moment the extraordinary precision required for these measurements. When L9859f tugs on its host star through gravitational attraction, it causes the star to move toward and away from us at speeds of just a few meters per second. To put this in perspective, that's slower than most people walk. Yet astronomers can detect this motion from a distance of 34 light-years across the vast emptiness of interstellar space. The instruments that make such measurements possible read like something from science fiction. The HARP spectrograph, perched high in the Chilean Andes, splits starlight into thousands of individual colours, each one carefully monitored for the telltale shifts that reveal planetary companions. Meanwhile, its even more sophisticated cousin, Espresso, pushes precision to levels that seemed impossible just a generation ago. These spectrographs work by measuring what astronomers call the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes by. When a star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. By tracking these minuscule color changes over months and years, astronomers can map out the gravitational influences of invisible worlds. But here's where the story becomes even more remarkable. The confirmation of L9859f required something called line-by-line radial velocity analysis, a technique so new that it was only introduced in 2022. Traditional methods analyze the average motion of a star based on broad sections of its spectrum. This new approach examines thousands of individual spectral lines simultaneously, each one providing its own tiny piece of evidence for planetary motion. It's rather like the difference between listening to an entire orchestra and picking out the contribution of each individual musician. The line-by-line technique allows astronomers to extract far more information from each observation, while also better distinguishing genuine planetary signals from the stellar activity that can masquerade as planetary companions. Red dwarf stars, you see, have their own personalities. They're prone to what astronomers politely call stellar activity, sudden flares, and magnetic storms that can temporarily change the star's brightness and spectrum. These stellar tantrums can create false signals that look remarkably like the signatures of orbiting planets. Learning to tell the difference between a real planet and an angry star requires both sophisticated algorithms and years of careful observation. The challenge is compounded by the fact that red dwarfs, particularly young ones, can be quite temperamental. They produce flares that dwarf anything our sun generates, explosive events that can temporarily double the star's brightness and flood nearby space with high-energy radiation. For planets orbiting close to such stars, these flares represent both a challenge and a clue to their potential habitability. Fortunately, L9859 appears to be what astronomers might call a well-behaved red dwarf. It's mature enough to have settled into a relatively stable pattern of energy output, though it still occasionally reminds us of its stellar nature with modest flares. This stability is crucial for the planets in its system, particularly for worlds like L9859F that might harbour liquid water. The habitable zone around any star is a rather fuzzy concept, defined more by possibilities than certainties. It represents the range of distances where a planet with the right atmospheric conditions might maintain liquid water on its surface. But that phrase carries a lot of assumptions about atmospheric pressure, composition, and circulation patterns. Around red dwarf stars, the habitable zone presents unique challenges and opportunities. Because these stars are so much cooler than our Sun, their habitable zones lie very close to the star. This proximity means that planets in the habitable zone likely experience what astronomers call tidal locking, where one side of the planet permanently faces the star while the other remains in perpetual darkness. At first glance, this might seem like a recipe for uninhabitable extremes. The day side would be scorched while the night side would be frozen solid. But recent climate modelling suggests that thick atmospheres could redistribute heat around the planet, potentially creating temperate zones along the boundary between day and night. These twilight regions, known as terminators, might offer the most hospitable conditions on tidally locked worlds. Here, the eternal sunset or sunrise could provide steady, moderate temperatures, while atmospheric circulation might create weather patterns unlike anything we see on Earth. The story becomes even more intriguing when we consider the diversity of the L9859 planets themselves. Each world in this system appears to have followed its own evolutionary path, despite forming from the same disk of material around the young star billions of years ago. The innermost planets, forged in the intense heat close to their star, appear to be primarily rocky worlds, though even they show surprising variety. L9859b, the innermost planet, might experience volcanic activity driven by tidal heating as it's stretched and squeezed by the gravitational pull of its star and neighbouring planets. This constant flexing could keep the planet's interior molten, driving geological processes that might create and maintain an atmosphere. Further out, the planets tell a different story. L9859d, with its unusually low density, appears to be what scientists call a water world. Computer models suggest that water might comprise as much as 30% of this planet's total mass, creating a world covered by oceans that could be hundreds of kilometers deep. Such water worlds challenge our Earth-centric view of habitability. While water is essential for life as we know it, these deep ocean planets might lack the geological cycles that help regulate Earth's climate over geological time. They might not have continents to weather and provide nutrients to their oceans, or volcanic activity to recycle carbon through their atmospheres. Yet they might also offer something Earth doesn't have: stability on cosmic timescales. Deep beneath kilometers of water, protected from stellar flares and cosmic radiation, these ocean worlds might provide havens for life that could persist for billions of years. The bottom of Earth's deepest ocean trenches teem with life that depends not on sunlight but on chemical energy from volcanic vents. Perhaps the deep oceans of worlds like L9859d could harbour similar communities of life. Then there's L9859F, the super-Earth that sits tantalizingly within the habitable zone. With roughly 3 times Earth's mass, this world would have a stronger gravitational field, one that could more easily retain a thick atmosphere, even in the face of stellar flares. Its 23-day orbit means it receives roughly the same amount of energy from its star that Earth receives from the Sun, but distributed very differently across its surface. If L9859F is tidally locked, as seems likely, its day side might experience temperatures hot enough to boil water, while its night side could be cold enough to freeze carbon dioxide. But in between, in those eternal twilight zones, conditions might be surprisingly Earth-like. Here, if the planet has retained an atmosphere and if that atmosphere can efficiently transport heat, we might find the cosmic equivalent of a perpetual spring evening, with temperatures perfect for liquid water. The James Webb Space Telescope has already begun to peer into the atmospheres of some planets in this system, searching for the chemical signatures that might reveal their true nature. These observations represent some of the most challenging work the telescope performs, attempting to detect the faint signals of planetary atmospheres around small, rocky worlds. Early results from Webb's observations of L9859d suggest the possible presence of sulfur compounds in its atmosphere. Sulfur chemistry in planetary atmospheres can tell us about volcanic activity, atmospheric circulation, and even potential biological processes. On Earth, certain sulfur compounds are produced by living organisms, though they can also arise from purely geological processes. The search for atmospheres around small, rocky planets pushes the very limits of what's possible with current technology. These worlds have thin atmospheres compared to gas giants, and they orbit close to bright stars that can overwhelm the faint signals astronomers are trying to detect. It's rather like trying to study a candle flame while standing next to a searchlight. Yet, Webb's unprecedented sensitivity in infrared light, combined with sophisticated analysis techniques, is beginning to reveal the atmospheric secrets of these distant worlds. Each successful detection adds another piece to the puzzle of planetary diversity and habitability around red dwarf stars. The implications of what we're learning from L9859 extend far beyond this single system. Red dwarf stars make up the vast majority of stars in our galaxy, and if many of them host planetary systems like this one, then the universe might be far more abundant in potentially habitable worlds than we ever dared imagine. But habitability, as we're learning, comes in many forms. The traditional concept of a habitable planet, one much like Earth with oceans and continents under a nitrogen-oxygen atmosphere, might represent just one possibility among many. Water worlds, tidally locked planets with temperate twilight zones, and even volcanic worlds with exotic atmospheres might all harbour their own forms of life. The story of L9859 reminds us that the universe is far more creative than our limited imaginations might suggest. In this single system, we find a collection of worlds that challenge our assumptions about planetary formation, atmospheric evolution, and the conditions that might support life. Each planet represents a different experiment in cosmic chemistry and physics, played out over billions of years under the gentle light of a red dwarf star. As we drift deeper into the mysteries of this remarkable system, let's pause for a moment to consider what it truly means to search for life among the stars. The L9859 system isn't just a collection of distant worlds, it's a window into the fundamental question that has haunted humanity since we first looked up at the night sky and wondered if we were alone. The search for life beyond Earth has always been a bit like searching for a whisper in a thunderstorm. We know what life looks like on our own world, but the universe might have written its story in languages we've never learned to read. Around red dwarf stars like L9859, that story might be written in dialects of chemistry and physics that would seem utterly alien to our earthbound perspective. Consider the peculiar dance of time that governs life in the L9859 system. On our planet, the rhythm of day and night has shaped every living thing, from the opening and closing of flowers to the sleep cycles that even now might be gently pulling you toward rest. But on a tidally locked world like L9859F, there are no days or nights as we understand them. Instead, there might be regions of eternal dawn, places where the sun hangs forever at the horizon, painting the sky in perpetual shades of amber and rose. What kind of life might evolve under such alien skies? Perhaps organisms that navigate by the fixed patterns of starlight, or creatures that have learned to harness the temperature gradients between the scorching dayside and the frozen nightside. Life, as we've learned from the most extreme environments on Earth, has an almost magical ability to find ways to thrive in conditions that would seem impossible to us. The water worlds of the L9859 system present their own fascinating possibilities. Imagine oceans so deep that their bottoms lie under pressures that would crush any submarine we've ever built. Yet within those depths, hydrothermal vents might create oases of warmth and chemical energy. On Earth, such vents support entire ecosystems that have never seen sunlight, communities of life that extract energy from the very rocks of the planet itself. But in the ocean depths of a world like L9859d, such communities might evolve over billions of years without any connection to the surface. They might develop forms of complexity and intelligence that we can barely imagine, perhaps even achieving something like civilization in the eternal darkness of their deep-sea realm. The idea isn't as far-fetched as it might seem. Here on Earth, some of the most sophisticated behaviors we observe occur in the deep ocean, where creatures navigate three-dimensional spaces with sonar, create tools from the materials around them, and communicate through chemical signals across vast distances. The volcanic world of L9859b presents yet another possibility. While the intense tidal heating might make this planet seem utterly hostile to life, it also creates conditions that might be remarkably similar to early Earth. Our own planet began as a molten ball of rock, constantly reshaped by volcanic activity and bombardment from space. Yet somehow, in those hellish conditions, the chemistry of life first began to stir. The sulfur-rich atmosphere that Webb might have detected around L9859d adds another layer to this cosmic puzzle. Sulfur chemistry can create some of the most exotic and colourful landscapes in the solar system. The volcanic moon Io, with its sulfur-painted surface of yellows, oranges and reds, gives us a glimpse of what such worlds might look like. But sulfur compounds also play crucial roles in the biochemistry of life on Earth, particularly in the deep-sea environments where life might have first evolved. What's particularly fascinating about sulfur is how it might behave in the atmosphere of a tidally locked planet. Unlike oxygen or carbon dioxide, sulfur compounds can create hazes and clouds that dramatically affect how heat and light move through an atmosphere. These sulfur clouds might act like a planetary thermostat, redistributing heat from the day side to the night side and creating more temperate conditions than we might otherwise expect. The James Webb Space Telescope's ability to peer into these distant atmospheres represents one of the most remarkable achievements in the history of astronomy. When light from L9859 passes through the atmosphere of one of its planets during a transit, different molecules absorb different wavelengths, creating a kind of chemical fingerprint that Webb can detect. It's rather like being able to identify the ingredients in a soup by analysing the steam that rises from the pot. Except the pot is 34 light-years away and the steam is made of starlight. But Webb's observations go beyond simply detecting what gases might be present in these atmospheres. The telescope can also measure how these gases are distributed, whether they're well mixed throughout the atmosphere or concentrated in particular regions. This information can tell us about weather patterns, atmospheric circulation, and even seasonal changes on these distant worlds. The seasonal patterns on tidally locked planets would be utterly unlike anything we experience on Earth. Instead of the familiar cycle of spring, summer, autumn, and winter, these worlds might experience changes driven by the varying distance from their star as they follow their slightly elliptical orbits. Even tiny changes in the amount of energy received from the star could trigger dramatic shifts in atmospheric circulation, creating weather patterns that migrate around the planet like slow-moving storms. The near-perfect circular orbits of the L9859 planets add another element of stability to this system. Highly elliptical orbits would create dramatic temperature swings as planets moved closer to and farther from their star during each orbit. The circular orbits we observe suggest that these worlds have settled into a gravitational equilibrium that has persisted for billions of years, providing the kind of stable conditions that might allow complex chemistry and perhaps life to evolve. This stability becomes even more remarkable when we consider the complex gravitational interactions between the 5 known planets. Each world influences its neighbours through subtle gravitational tugs, creating what astronomers call orbital resonances. These resonances help keep the planets in their stable configurations, like cosmic clockwork that has been ticking steadily since the system formed. The precision with which we can now measure these orbital interactions is truly extraordinary. By timing the transits of the inner planets to within minutes, astronomers can detect the gravitational influences of the outer, non-transiting planets. It's rather like deducing the presence of invisible dancers by watching how their partners move, reading the story of the entire system in the slight variations of planetary timing. These transit timing variations also tell us about the masses and densities of the planets, crucial information for understanding their composition and structure. The low density of L9859d, for instance, immediately suggested that this world contains large amounts of water or other light materials. Computer models of planetary interiors can then tell us how much water might be present and how it might be distributed between the surface, atmosphere, and deep interior. The diversity of planetary compositions within the L9859 system provides a natural laboratory for studying how planets form and evolve. The inner planets, forged in the intense heat close to their star, are primarily rocky, while the outer planets show increasing amounts of water and other volatile materials. This pattern matches theoretical models of planetary formation, where water and other light compounds can only condense and survive at greater distances from the hot central star. But the L9859 system also holds surprises that challenge our understanding. The presence of what might be significant amounts of water on worlds so close to their star suggests that planetary formation around red dwarfs might follow different rules than we see around sun-like stars. Perhaps the lower temperatures and longer formation timescales around these small stars allow volatile materials to survive in regions where they would be quickly lost around hotter, more massive stars. The age of the L9859 system adds another dimension to these questions. Red dwarf stars evolve so slowly that even ancient systems might still be in the early stages of their stellar development. Unlike our Sun, which will eventually expand into a red giant and make Earth uninhabitable, red dwarfs like L9859 could maintain stable energy output for trillions of years, providing vast amounts of time for life to evolve and develop complexity. This longevity raises profound questions about the potential for intelligence and civilization around red dwarf stars. If life can arise on the planets of such systems, it might have billions of years longer than terrestrial life to evolve and develop. The implications are staggering when we consider that human civilization has existed for only a few thousand years, and our species for only a few 100,000 years. The search for signs of life around stars like L9859 is pushing the boundaries of what's possible with current technology, but it's also preparing us for even more ambitious projects in the future. Proposed space telescopes with names like Habitable and Louvois would have the sensitivity to directly image Earth-sized planets around nearby stars, potentially revealing not just their atmospheric compositions, but even surface features like oceans, continents, and weather patterns. Such observations might even detect what astronomers call biosignatures, combinations of gases that would be extremely difficult to explain without biological processes. The simultaneous presence of oxygen and methane in an atmosphere, for instance, would be a strong indicator of life, since these gases react with each other and would quickly disappear unless constantly replenished by living organisms. But perhaps the most intriguing possibility is the detection of what might be called technosignatures, evidence of technological civilizations. These might include artificial light on the night sides of tidally locked planets, atmospheric pollution from industrial processes, or even massive engineering projects that alter the energy output of entire star systems. The L9859 system, with its 5 diverse worlds and potential for harboring multiple forms of life, represents exactly the kind of target where such searches might prove most fruitful. A system with several potentially habitable planets might offer multiple opportunities for life to arise and evolve, perhaps even leading to communication or interaction between different worlds within the same stellar system. As we continue to study L9859 and systems like it, we're not just learning about distant worlds, we're gaining new perspectives on our own planet and our place in the cosmic story. Every new discovery reminds us that Earth, while precious and unique in its own way, might not be as unusual as we once believed. The universe might be filled with worlds where different forms of life have learned to thrive under alien suns, in deep oceans, or in the eternal twilight between day and night. The gentle red light of L9859 has been shining steadily for billions of years, warming its family of worlds in the constellation of Volans. As you drift towards sleep tonight, perhaps you can imagine that light crossing the vast emptiness of space, carrying with it the possibility of stories we have yet to learn, of life forms we have yet to discover, and of answers to questions we have only just begun to ask. In the grand tapestry of the cosmos, the L9859 system represents just one thread, but it's a thread that connects us to the deepest mysteries of existence itself. And as our technology continues to advance, as our understanding deepens, and as our search for life beyond Earth becomes ever more sophisticated, systems like this one will continue to surprise us, challenge us, and remind us that the universe is far stranger and more wonderful than our earthbound imaginations might suggest. The story of these 5 worlds is still being written, each new observation adding another chapter to our understanding of what it means to be a planet, what it means to be alive, and what it means to search for our place among the stars. And perhaps in the quiet moments before sleep takes hold, we can find comfort in knowing that somewhere out there, under the gentle light of a red dwarf star, the cosmic experiment of existence continues to unfold in ways that would fill us with wonder if we could only see them clearly. The search for atmospheric signatures around these distant worlds has become something of an astronomical art form, requiring instruments so sensitive they can detect changes in starlight, equivalent to distinguishing the glow of a firefly from the beam of a lighthouse. When astronomers turn Webb's golden mirror toward the L9859 system, they're attempting something that would have seemed like pure fantasy just a generation ago. They're trying to sniff the air of worlds that exist as mere points of light, even through our most powerful telescopes. The process itself is beautifully elegant in its simplicity, even as it pushes technology to its absolute limits. As one of the inner planets crosses in front of L9859, starlight filters through whatever atmosphere the planet might possess. Different molecules absorb different wavelengths of this light, creating what astronomers call an absorption spectrum. It's rather like how sunlight passing through coloured glass creates stained glass windows, except here the colours tell us about alien chemistry taking place trillions of miles away. But detecting these atmospheric fingerprints requires extraordinary patience and precision. The signals astronomers are hunting for are incredibly faint, often buried in noise and interference from Earth's own atmosphere, from the spacecraft's instruments, and from the natural variability of the star itself. It's a bit like trying to hear a whispered conversation in a crowded restaurant while wearing earmuffs, except the conversation is happening on another continent. The early atmospheric observations of the L9859 planets have yielded tantalizing hints rather than definitive answers. Some measurements suggest the possible presence of sulfur compounds around L9859d, while others remain frustratingly inconclusive. This uncertainty isn't a failure of the instruments or the astronomers using them. It's simply the reality of pushing the boundaries of what's possible with current technology. Each non-detection tells us something valuable too. When Hubble observations failed to find clear evidence of thick atmospheres around the inner planets, that absence became data in itself. It suggests that these worlds, bombarded by stellar radiation and perhaps stripped by ancient stellar flares, might have lost whatever atmospheres they once possessed. Or perhaps they never had substantial atmospheres to begin with, forming too close to their star to accumulate the volatile materials that create the thick, protective blankets of gas we see around worlds like Earth and Venus. The story becomes more intriguing when we consider what kinds of atmospheres might actually survive around a red dwarf star. Traditional models suggested that the intense ultraviolet radiation and stellar flares common to these stars would strip away planetary atmospheres relatively quickly, leaving behind airless, lifeless rocks. But recent computer simulations paint a more complex picture, one where the outcome depends critically on the planet's mass, magnetic field, and the specific behavior of its host star. Super-Earths like L9859F have a significant advantage in this cosmic struggle. Their stronger gravitational fields can hold onto atmospheric gases more tenaciously than smaller worlds, even in the face of stellar tantrums. A planet with 3 times Earth's mass creates a gravitational well deep enough to retain water vapor, carbon dioxide, and other crucial atmospheric components over billions of years. The magnetic field question adds another layer of complexity to the habitability puzzle. Earth's magnetic field acts like an invisible shield, deflecting much of the solar wind and cosmic radiation that would otherwise strip away our atmosphere. We don't yet know whether any of the L9859 planets possess similar magnetic protection, but their masses and likely compositions suggest that at least some of them might generate magnetic fields through the motion of molten iron in their cores. The tidal locking that likely affects planets in the L9859 system creates its own atmospheric dynamics that we're only beginning to understand. On a tidally locked world, the day side receives constant stellar heating, while the night side radiates heat away to space. This temperature difference would drive powerful atmospheric circulation patterns, with hot air rising on the day side and cold air sinking on the night side, creating global wind patterns unlike anything we see on Earth. These circulation patterns could actually help make tidally locked planets more habitable than we might expect. If the atmosphere is thick enough and the circulation efficient enough, heat could be transported from the scorching day side to the frozen night side, moderating temperatures across the entire planet. Computer models suggest that even relatively thin atmospheres could create temperate zones along the terminator, the boundary between day and night. The chemistry of these alien atmospheres might be equally exotic. On the day side of a tidally locked planet, intense stellar radiation could drive chemical reactions that would be impossible in Earth's more moderate environment. Water molecules might be split apart into hydrogen and oxygen, with the light hydrogen escaping to space while the heavier oxygen remains behind. Over geological time, this process could create oxygen-rich atmospheres that might look like biosignatures but actually result from purely physical processes. On the night side, different chemistry might dominate. Without the energy input from stellar radiation, atmospheric gases might condense and freeze, creating vast deposits of frozen carbon dioxide, water ice, or other compounds. These frozen reservoirs could act like planetary batteries, storing volatile materials during the long night and potentially releasing them back into the atmosphere through various mechanisms. The seasonal cycles on these worlds would be governed not by axial tilt, as they are on Earth, but by the slight eccentricity of their orbits. Even the nearly circular orbits we observe in the L9859 system have tiny variations that could drive atmospheric changes. As a planet moves slightly closer to or farther from its star during each orbit, the delicate balance between day-side heating and night-side cooling could shift, triggering planet-wide weather patterns that migrate around the globe like slow-motion storms. Recent advances in theoretical modelling have revealed just how sensitive these atmospheric systems might be to small changes. A variation of just a few % in stellar energy could trigger dramatic shifts in atmospheric circulation, potentially switching a planet between different climate states. This sensitivity means that planets around red dwarf stars might experience much more dynamic and variable climates than we see on Earth, with implications for any life that might evolve there. The water worlds in the L9859 system present their own atmospheric puzzles. A planet like L9859d, with its deep global ocean, might have an atmosphere dominated by water vapor. The interactions between such a thick, steamy atmosphere and the underlying ocean could create weather patterns of extraordinary complexity. Imagine storms that span entire hemispheres with clouds of water vapor rising kilometers into the atmosphere before condensing and falling back as torrential rains that never quite reach the surface, evaporating again in the hot, humid air. Such water worlds might also experience what scientists call a runaway greenhouse effect, where water vapor in the atmosphere traps so much heat that the oceans begin to boil away. This process might already be underway on Venus, where a thick atmosphere of carbon dioxide and water vapor has created surface temperatures hot enough to melt lead. Whether the water worlds of L9859 can avoid this fate depends on delicate balances between stellar heating, atmospheric circulation, and the planet's ability to radiate heat back to space. The volcanic activity that might occur on worlds like L9859b adds yet another variable to the atmospheric equation. Volcanic outgassing could continuously replenish atmospheres that might otherwise be stripped away by stellar activity. On Earth, volcanic activity has played a crucial role in maintaining our atmosphere over geological time, releasing water vapor, carbon dioxide, and other gases that help regulate our planet's climate. But volcanic activity on a tidally locked planet might follow very different patterns than what we see on Earth. The constant tidal heating would focus geological activity in specific regions, potentially creating volcanic hotspots that persist for millions of years. These regions might act like atmospheric factories, continuously pumping gases into the air and creating complex chemical cycles that we're only beginning to understand. The search for biosignatures in the atmospheres of the L9859 planets represents one of the most ambitious goals in modern astronomy. On Earth, life has dramatically altered our atmosphere, filling it with oxygen through photosynthesis and creating complex chemical cycles that would be impossible on a lifeless world. The simultaneous presence of oxygen and water vapor in Earth's atmosphere, for instance, creates a chemical signature that would be extremely difficult to explain without biological processes. But detecting such signatures around distant planets requires us to think carefully about what life might look like under alien conditions. The forms of life that might evolve around a red dwarf star, in deep oceans, or on tidally locked worlds might create very different atmospheric signatures than the oxygen-rich air we breathe. Perhaps life on these worlds would be based on sulfur chemistry rather than carbon chemistry, creating atmospheric signatures that we're only beginning to learn how to recognize. The James Webb Space Telescope's ongoing observations of the L9859 system represent just the beginning of a new era in atmospheric characterization. Future space telescopes, with even greater sensitivity and specialized instruments, will be able to detect increasingly subtle atmospheric signatures. They might even be able to measure the day-night temperature differences on tidally locked planets, map cloud patterns, and detect seasonal changes in atmospheric composition. These future observations might also reveal indirect signs of habitability that we haven't yet learned to recognize. The presence of industrial pollutants in an atmosphere, for instance, might indicate technological civilization. Artificial lighting on the night side of a tidally locked planet could be detectable as a faint glow in infrared light. Even large-scale engineering projects like solar collectors or atmospheric processors might leave detectable signatures in the light from distant worlds. The L9859 system, with its diverse collection of planets and potential for multiple forms of habitability, represents an ideal laboratory for testing these new techniques. Each planet offers a different experiment in atmospheric science and astrobiology, from the potentially volcanic world of L9859b to the possible water world of L9859d to the temperate super-Earth L9859f. As our understanding of these distant atmospheres deepens, we're also gaining new perspectives on our own planet's atmosphere and climate. The extreme conditions around red dwarf stars help us understand the boundaries of habitability and the factors that make Earth's climate so remarkably stable. Every new discovery reminds us of how precious and unusual our own atmospheric conditions might be, even as it suggests that life might find ways to thrive under conditions we never imagined possible. The story of atmospheric science around red dwarf stars is still being written, with each new observation adding to our understanding of how planets and atmospheres evolve under different stellar conditions. The L9859 system, glowing quietly in the constellation of Volans, continues to challenge our assumptions and expand our vision of what might be possible in the cosmic dance between stars, planets, and the thin veils of gas that separate the cold vacuum of space from the warm surfaces where life might take hold. In the gentle rhythm of discovery that marks our exploration of distant worlds, each measurement and each spectrum adds another note to the symphony of knowledge we're composing about our place in the universe. The atmospheres of the L9859 planets, whether thick or thin, exotic or familiar, all tell part of the larger story of how matter and energy, time and chance have conspired to create the conditions where consciousness can emerge to contemplate its own cosmic origins. And perhaps, as you settle into the quiet moments before sleep, you might imagine the invisible dance of molecules in those distant atmospheres, the slow circulation of alien air around worlds we may never visit, but can now, for the first time in human history, begin to truly understand. The universe reveals its secrets slowly, in whispers of starlight and the patient analysis of spectra. But each revelation brings us closer to answering the ancient question of whether we are alone among the stars. The gentle persistence of our search for life among the stars has led us to develop increasingly sophisticated ways of listening to the whispers of distant worlds. Each new technique, each refinement in our instruments, brings us closer to that moment when we might detect the unmistakable signature of biology thriving under an alien sun. The L9859 system has become something of a proving ground for these methods, a nearby laboratory where we can test the limits of what's possible with current technology while preparing for even more ambitious searches in the years to come. One of the most intriguing aspects of studying the L9859 planets lies in what astronomers call temporal variability. Unlike the steady signals we might expect from lifeless worlds, planets with active atmospheres, weather systems, or even biological processes might show changes over time. These variations could manifest as subtle shifts in atmospheric composition between different observations, seasonal changes driven by orbital mechanics, or even more dramatic alterations that might indicate geological or biological activity. The challenge of detecting such changes requires us to observe these distant worlds repeatedly over months and years, building up a picture of their atmospheric behavior over time. It's rather like trying to understand a person's character by catching glimpses of them through a distant window, noting how they change with the seasons, how they respond to different conditions, and what patterns emerge from their daily rhythms. Early observations of the L9859 system have begun to hint at such variability, though the signals remain tantalizingly faint. Some measurements suggest possible changes in the atmospheric properties of L9859d between different observation epochs, though astronomers remain cautious about interpreting these variations. The difference could indicate active weather systems, seasonal changes, or even measurement uncertainties that we're still learning to account for. The concept of planetary weather on worlds so different from Earth challenges our terrestrial intuitions about how atmospheres behave. On a tidally locked planet like L9859f, weather patterns would be driven by the constant temperature difference between day and night sides rather than by seasonal changes. Imagine permanent storm systems that circle the globe along the Terminator line, where hot air from the day side meets cold air from the night side in an eternal battle between light and darkness. These Terminator storms could create their own unique atmospheric chemistry. The constant mixing of air masses with very different temperatures and compositions might drive chemical reactions that would be impossible in more stable atmospheric conditions. Lightning in these eternal storms could provide the energy needed to create complex organic molecules, potentially seeding the atmosphere with the building blocks of life. The magnetic environment around red dwarf stars adds another layer of complexity to our understanding of these distant atmospheres. Unlike our Sun, which has a relatively stable magnetic field, red dwarfs can experience dramatic magnetic events that dwarf anything in our solar system. These magnetic storms can accelerate particles to incredible energies, creating radiation environments that would be lethal to life as we know it. Yet these same magnetic interactions might also create unexpected opportunities for habitability. The interaction between stellar magnetic fields and planetary atmospheres could generate powerful auroras that extend far beyond what we see on Earth. These alien auroras might not only create spectacular light shows, but also drive atmospheric chemistry in ways that could support or even create conditions favorable to life. Recent computer simulations have revealed that the magnetic interactions between red dwarf stars and their planets might be far more complex than previously imagined. Some models suggest that planets with strong magnetic fields might actually channel stellar wind particles toward their polar regions, creating focused heating that could melt polar ice caps or drive atmospheric circulation patterns. Other models propose that magnetic field interactions could create stable plasma structures that act like atmospheric umbrellas, protecting certain regions of a planet from harmful radiation while leaving others exposed. The study of these magnetic effects requires observations across multiple wavelengths of light, from radio waves to X-rays. Each wavelength reveals different aspects of the magnetic dance between star and planet, building up a three-dimensional picture of how these interactions might affect habitability. The L9859 system, with its multiple planets at different distances from their star, provides an ideal natural laboratory for studying how these magnetic effects vary with orbital distance. As we peer deeper into the atmospheric mysteries of the L9859 worlds, we're also confronting fundamental questions about the nature of habitability itself. The traditional concept of the habitable zone, that narrow band around a star where liquid water can exist, increasingly seems like just the beginning of a much more complex story. Habitability, we're learning, depends on an intricate web of factors that include atmospheric composition, magnetic fields, stellar activity, orbital dynamics, and perhaps most importantly, the ability of a planet to maintain stable conditions over the vast timescales required for life to evolve. The super-Earth L9859F sits at the center of these considerations, a world that challenges many of our assumptions about what makes a planet suitable for life. With 3 times Earth's mass, this world would have a surface gravity about twice what we experience here. Walking on such a world would feel like carrying another person on your back, and the atmospheric pressure at the surface could be several times greater than what we're accustomed to. Yet these seemingly hostile conditions might actually favor the development and maintenance of life. Higher surface pressure would allow liquid water to exist at higher temperatures, potentially creating hot springs and geysers that could serve as cradles for early life. The stronger gravity would help retain atmospheric gases over geological time, preventing the slow leakage to space that might have stripped away the atmospheres of smaller worlds. The atmospheric circulation on such a high-gravity world would follow patterns unlike anything we see on Earth. Denser air would flow more slowly but carry more heat and moisture, potentially creating weather systems that persist for much longer periods. Storm systems that might last days on Earth could persist for weeks or months on a super-Earth, creating stable climate patterns that could support complex ecosystems. The seasonal patterns on L9859F would be governed by the slight eccentricity of its orbit rather than by axial tilt, as they are on Earth. As the planet moves through its 23-day orbit, tiny variations in its distance from the star could drive atmospheric changes that propagate around the globe like slow-motion waves. These orbital seasons might create migration patterns for any life forms that evolve there, with organisms following temperature and humidity gradients as they shift around the planet. The potential for life on such worlds has led astronomers to develop increasingly sophisticated models of planetary habitability that go far beyond simple temperature calculations. These models consider factors like atmospheric circulation, ocean dynamics, geological activity, and even the potential for complex chemistry to arise in different environmental niches. Each new refinement in these models reveals new possibilities for life to emerge and thrive under conditions that might seem impossibly alien from our Earthbound perspective. The deep ocean world of L9859d presents perhaps the most intriguing possibilities for exotic forms of life. Computer models suggest that this planet's oceans could be hundreds of kilometers deep, creating pressure environments that exceed anything found on Earth. At such depths, water itself begins to behave differently, forming exotic phases of ice that remain solid at temperatures well above the normal freezing point. These high-pressure ice formations could create complex geological structures within the planet's ocean, perhaps forming underwater mountain ranges or cavern systems that could provide stable environments for life to evolve. The boundary layers between different phases of water and ice might concentrate organic molecules and provide energy gradients that could power biological processes. The chemistry of such deep oceans would be dominated by the interaction between water and rock at the ocean floor. Unlike Earth's oceans, which are relatively shallow and strongly influenced by atmospheric processes, the deep oceans of L98 to 59d might be largely isolated from any surface atmosphere. Instead, their chemistry would be governed by the slow leaching of minerals from the rocky ocean floor and by any hydrothermal activity driven by the planet's internal heat. Such isolated ocean systems might evolve their own unique forms of biochemistry, potentially based on different chemical elements than the carbon-based life we know on Earth. Silicon-based chemistry, for instance, becomes more favorable under high-pressure conditions, potentially creating forms of life that incorporate rock-like structures into their biology. These silicon-based organisms might build their bodies from the same materials as the ocean floor, creating living reefs or coral-like structures that could span entire ocean basins. The possibility of intelligent life evolving in such deep ocean environments raises fascinating questions about how consciousness might develop under conditions so different from our own. Without sunlight to drive photosynthesis, such life would depend entirely on chemical energy sources, potentially developing senses and cognitive abilities adapted to a world of eternal darkness, chemical gradients, and pressure waves. Communication in such environments might rely on chemical signals, pressure waves, or even electrical impulses conducted through the water itself. An intelligent species that evolved in the deep oceans of L9859d might develop technologies based on biological processes rather than the metal and silicon technologies we use on Earth. They might cultivate living structures that serve as both habitat and tool, creating a form of civilization that would be almost unrecognizable to us. The volcanic world of L9859b, with its tidally heated interior and potential for active geology, represents yet another pathway for life to emerge under extreme conditions. The constant flexing and heating caused by gravitational interactions with its star and neighboring planets could maintain volcanic activity for billions of years, creating a dynamic environment where new chemical compounds are constantly being formed and destroyed. Such volcanic activity could drive atmospheric processes that create surprisingly complex chemistry. Sulfur compounds released from volcanic vents could interact with water vapor and other atmospheric gases to create clouds of exotic chemicals that might serve as the raw materials for biological processes. The energy released by volcanic activity could power chemical reactions that would be impossible under more stable conditions. Recent studies of extremophile organisms on Earth have revealed life forms that thrive in conditions that closely resemble what we might find on volcanic worlds like L9859b. These organisms can survive in temperatures that would kill most life forms, in highly acidic or alkaline conditions, and even in environments with high levels of radiation. Some can extract energy directly from inorganic chemical reactions, independent of sunlight or organic matter. The discovery of these extremophiles has revolutionized our understanding of the conditions under which life might arise and persist. If life can thrive in the volcanic hot springs of Yellowstone, in the acidic rivers of mining regions, or in the radiation-soaked environments around nuclear reactors, then the harsh conditions on worlds like L9859b might not be barriers to life, but rather opportunities for different forms of biology to evolve. The ongoing search for biosignatures in the L9859 system has begun to incorporate these new understandings of extremophile biology. Rather than looking only for the oxygen and water vapor signatures that might indicate Earth-like life, astronomers are now developing techniques to detect the chemical signatures of more exotic forms of biology. Sulfur compounds, methane, phosphine, and other gases that might be produced by extremophile organisms are all becoming targets for future atmospheric studies. The James Webb Space Telescope's unprecedented sensitivity in infrared light makes it particularly well suited for detecting these exotic biosignatures. Many of the chemical compounds produced by extremophile organisms have strong absorption features in the infrared, making them potentially detectable even in the thin atmospheres of small, rocky planets. Each new observation adds to our growing database of atmospheric compositions around nearby stars, building toward the day when we might recognize the unmistakable signature of biology thriving under alien conditions. The L9859 system has also become a testing ground for future space missions that might directly search for signs of life around nearby stars. Proposed space telescopes with names like the Habitable Exoplanet Observatory and the Large Ultraviolet Optical Infrared Surveyor would have the sensitivity to directly image Earth-sized planets around nearby stars, potentially revealing surface features, weather patterns, and even seasonal changes that might indicate biological activity. These future missions would represent a qualitative leap forward in our ability to study distant worlds. Instead of inferring planetary properties from tiny dips in starlight or subtle shifts in stellar spectra, we would be able to see these worlds as actual disks of light, potentially revealing oceans, continents, cloud patterns, and even the glint of sunlight reflecting off-surface water. Such direct imaging might even detect the seasonal greening and browning of vegetation, the unmistakable signature of a living world. The technological challenges involved in such observations are staggering. Directly imaging an Earth-sized planet around a nearby star is like trying to photograph a firefly sitting next to a lighthouse from a distance of several thousand miles. The light from the planet is billions of times fainter than the light from its star, requiring extraordinary techniques to block out the stellar glare while preserving the faint planetary signal. Recent advances in adaptive optics, coronagraph technology, and space-based interferometry are bringing these seemingly impossible observations within reach. Ground-based telescopes are already beginning to directly image large young planets around nearby stars, and space-based missions in the coming decades will extend these capabilities to smaller, more Earth-like worlds. The L9859 system, with its multiple potentially habitable planets and its proximity to Earth, represents an ideal target for these future direct imaging missions. The system's compact architecture means that multiple planets might be visible simultaneously, allowing astronomers to compare their properties and potentially detect interactions between different worlds within the same system. The possibility of detecting signs of technology around distant stars has also captured the imagination of astronomers studying systems like L9859. Advanced civilizations might leave detectable signatures in their planetary atmospheres through industrial activity, artificial lighting, or large-scale engineering projects. The search for such techno-signatures represents a new frontier in the search for extraterrestrial intelligence, one that might be more successful than traditional approaches based on radio signals or deliberate attempts at communication. A technological civilization on a tidally locked planet like L9859f might create artificial lighting on the night side of their world, potentially detectable as a faint infrared glow against the cosmic background. Massive solar collection arrays or atmospheric processing facilities might alter the planet's energy balance in ways that could be measured from interstellar distances. Even the waste heat from large-scale industrial activity might be detectable through careful analysis of the planet's thermal emission. The diversity of the L9859 system raises the intriguing possibility that multiple forms of life might have evolved within a single stellar system. If life arose independently on several of these worlds, they might have followed very different evolutionary paths, potentially leading to biological diversity that exceeds anything we see on Earth. The possibility of communication or even contact between different life forms within the same star system opens up scenarios that stretch the boundaries of both science and imagination. Such interplanetary biology might follow patterns that we're only beginning to understand through studies of Earth's own biosphere. The exchange of materials between different environments, through meteorite impacts or other mechanisms, could spread life from one world to another within the same system. This process, called panspermia, might create biological connections between planets that could persist over geological timescales. The gravitational interactions between the planets in the L9859 system could facilitate such exchanges. Impacts on one world could launch material into space that might eventually reach the surfaces of neighboring planets, potentially carrying with it the seeds of life. Over millions of years, this process could create a system-wide biosphere where life on different worlds shares common origins but evolves along different paths. As our understanding of the L9859 system continues to deepen through ongoing observations and theoretical modelling, we're confronting fundamental questions about the nature of life itself and our place in the cosmic order. Each new discovery challenges our assumptions about what makes a world habitable and expands our vision of the conditions under which consciousness might arise. The red dwarf stars that populate our galaxy represent the most common stellar environment in the Milky Way, and if systems like L9859 are typical, then the universe might be far more abundant in potentially habitable worlds than we ever dared imagine. The implications for the prevalence of life, intelligence, and even technological civilization could be profound, suggesting that we live in a universe where consciousness and complexity are not rare accidents, but common outcomes of cosmic evolution. The search for life around red dwarf stars like L9859 is teaching us that habitability comes in many forms, from the familiar blue-green worlds of our imagination to exotic water worlds, volcanic hellscapes, and tidally locked planets with eternal sunrises. Each possibility expands our understanding of what it means to be alive and challenges us to think beyond the comfortable boundaries of our Earth-centered perspective. In the quiet moments before sleep, as we contemplate these distant worlds spinning silently around their crimson sun, we might find comfort in the possibility that consciousness like our own might be looking back across the void, contemplating the mysteries of existence under different skies. The L9859 system reminds us that we are part of something much larger than ourselves, participants in a cosmic story that is still being written among the stars. The gentle light of L9859 continues its ancient journey across space, carrying with it the secrets of worlds we are only beginning to understand. And perhaps, in the careful analysis of that light, in the patient accumulation of spectra and observations, we will find the answers to questions that have haunted humanity since we first looked up at the night sky and wondered if we are alone. Night sky and wondered if we are alone.